All right, so we've got a couple more things from our chapter 10 that people were asking me about that I didn't cover. I didn't cover things about circles, so things about, say, like the sector or the arc. And sector and arc are just vocab words that talk about if you aren't doing a full circle, instead you're just doing part of a circle, the part of the circle that is the circumference, like the crust of the pizza slice there, that's called an arc. Whereas the part that is the area, that's not a great color contrast. The part that's the area on the inside is called the sector. And here's the big idea. You know the formula for a full circle. We know that for a full circle, the area is pi r squared, and the circumference of a full circle is 2 pi r. Which, by the way, now you've probably learned some calculus at this point, you should think, oh, that the circumference is the derivative of the area. Which makes sense, because if you make the area a little bit bigger, you're basically adding another circumference around the circle. So how do we change this formula to deal with the arc instead? So what we do is we focus on this angle right there called theta. And think about it, angle represents the fraction of the full circle that is that we're focusing on here. Okay, so here's how I can adjust the area to be, or sorry, not the area, but the circumference to be an arc length. Instead of looking at the full circle, so the arc length, we're not looking at a full circle anymore. So what we're doing is we're looking at a fraction of the circle. And the fraction of the circle that we're looking at is theta. A full circle in terms of degrees is 360. A full circle in terms of radians is 2 pi. So that's the fraction of the circle that we're looking at. And the circumference of the whole circle is 2 pi r. This is just like saying, if I was looking at a half of a circle, I would go a half of 2 pi r. If I was looking at a quarter circle, I would do a quarter of 2 pi r. We're just generalizing that and saying we're looking at theta out of 2 pi, and the thing that we're measuring is 2 pi r. So 2 pi down here cancels 2 pi up here, and we just get theta times r. Now I want to be very clear here that the arc length equaling theta times r, this theta must be radians. If I had done this formula using degrees, I would have done theta divided by 360. And the 360 would not cancel the 2 pi r. You can still use that formula. If you have your answers in degrees, you can go theta divided by 360 times 2 pi r. That'll give you the arc length. But you just need to make sure that you're using this formula in the formula packet. You're only using that if your theta is in radians. Okay? And we can convert between radians and degrees because we remember that 2 pi radians is equal to 360 degrees. So that means that 1 radian is 360 degrees divided by 2 pi. Some people like to simplify that down to say that 1 radian is 180 degrees over pi. And that means that if you wanted to know how much, say, 10 radians is, you'd multiply both sides by 10. If you wanted to know x radians, you'd multiply both sides by x. Okay. Now instead of the arc length, what if I was looking at the sector? Then I'm going to take the area, and I'm going to do basically the same thing, that the sector area is theta over 2 pi, the fraction of the circle you're looking at, times pi r squared. Similarly, you can cancel out the pi's, but there's no 2 to cancel out. So in your formula packet, I think it'll just say theta r squared over 2, or r squared theta over 2. And again, theta must be radians. Must be radians. Okay? Great. So let's look at an example of something that we could do here. So let's say that we've got a circle like this. call this O, call this T, and then we're drawing a line all the way over here to point A. We're making a triangle like that, and we want to know this shaded area, okay? So here's what I'm thinking. If I want to know the shaded area, I'm going to do the triangle ATO minus the sector, because that part was not shaded. Okay? So here's what we were told. We were told that OA is 12, and we were told that the radius of the triangle, or the radius of the circle, is 6. Okay, so we want to know some different angles here. And then the other thing that we're told is that the AT here is tangent to the circle. And so if it's tangent to the circle, that's a really big clue. That means this has to be a right angle. So we've got a right triangle here, okay? So if we've got a right triangle, we can figure out any angle we want. So I'm going to look at this angle right here as angle theta. That angle is adjacent to 6, and the 12 is the hypotenuse of that triangle. So adjacent and hypotenuse means I know that I'm going to do cosine of theta equals adjacent over hypotenuse, and I'm going to do inverse cosine, but I'm going to make sure that I'm in degree mode, or I'm in radian mode first, because like I was just saying a second ago, those formulas like you to be in radian mode. So I'm going to do inverse cosine of 6 over 12. You could have reduced that to be a half. So we get that theta is the inverse cosine, so it's about 1.047. I'm not going to round that answer when I do my calculations. I'm going to try to save it. Okay, so what's the area of the triangle? The area of the triangle is 1/2 A B sine of theta, so the saved answer from before. What's the area of the sector? The area of the sector is 2 pi over theta over 2 pi times pi r squared. And I guess we can cancel out the pi's there. Okay, so here's how we're going to do it. We're going to go, I'm just going to show you exactly how I type it in. 1/2 times 6 times 12 sine of the answer, so that's the first part of it, minus the answer over 2 times 6 squared. That right there gives you the shaded area. 12.33, rounded like that. Okay, so there you go. There's a little bit of stuff about some circle formulas and then an example problem. Please let me know what else you want me to do.